Well, welcome, everyone. Is this on? Yes. So I'm Mike Walter, and I'm the director of the Geophysical Lab. And on behalf of everyone here at the Broad Branch Road campus of Carnegie Science, I'd like to welcome you for tonight's neighborhood lecture. It's a real pleasure to introduce tonight's speaker, who is Sally June Tracy. And Sally is the most recent addition to the GL staff. She just arrived in January. Sally did her bachelor's degree at Occidental College. From there, she went on to California Institute of Technology, where she got both a master's degree and a PhD in materials science. Somewhere along the way, I think she got seduced by sort of earth and planetary science, and so she's sort of straddling this domain between materials and Earth and planets. Of course, Earth and planets are made of materials as well. And Sally represents sort of a bit of a new frontier for us at the Geophysical Lab, and I won't be a spoiler, and I'll let Sally tell you about it, but she explores a pressure, temperature, time regime, which is quite unique and allows Sally and her collaborators to explore a whole different regime of pressure, temperature, space. And I think with that, I'll turn it over to Sally, who's going to talk us about shocking minerals tonight.
It's working. Well, thank you, Mike, so much for the introduction. And thank you, everyone, for joining us this evening. And so my plan tonight is to talk a little bit about the experimental techniques that we use in order to generate shock waves and study materials in the laboratory, and then hopefully give you a flavor of a few of the different types of scientific questions that we can address with these types of techniques. And so my research focuses on using shock waves to study the crystal structures of materials at ultra-high pressures and temperatures. And so using these types of shock wave-driven techniques, we can address a range of scientific questions, ranging from things like understanding meteorite impacts and other types of natural impact events, to better characterizing the internal structure of, for example, large planetary bodies like extrasolar planets. And so in many ways, sort of common theme of my research is the idea of pushing on extremes in many directions. And this is because I'm interested in studying the properties of materials at thousands of degrees Fahrenheit and understanding how materials behave at millions of times greater than the atmospheric pressure we experience on Earth. And in order to study materials in these types of extreme environments, it requires that we develop tools where we, for example, are able to accelerate projectiles at incredible speeds, up to maybe 20 times the speed that a rifle might fire a bullet, for example, or alternatively turn to using extremely powerful lasers with a power output that might rival something similar to the entire US electrical grid. And so it's pretty impressive that we are able to harness these types of tools in order to generate such extreme conditions. But on top of that, these experiments tend to only last for a very short amount of time. And so in addition to this, we're required to develop techniques in which we can probe material on very, very fast timescales on the order of a nanosecond, which is a billionth of a second, up to the microsecond regime, which is a millionth of a second. And so the technique that I'll focus on talking about tonight is taking advantage of extremely bright light in order to sort of develop pictures of the structures of these materials. And so we're taking advantage of this very bright synchrotron radiation that is 1,000,000 to 1,000,000,000,000 times brighter than the radiation we receive from the sun on Earth. And so I'm in particular interested in understanding the atomic level crystal structure of materials and how this adopts and changes in these types of incredibly extreme environments. And so most solids can be described as a crystal, and that simply means that the solid is composed of atoms that are arranged in a repeating pattern that extends in 3 dimensions. And that repeating solid structure is held together by a network of electronic bonds that can be thought of as sort of a scaffolding of forces that connect the component atoms. And as it turns out, when we increase the temperature and pressure that a crystal is subjected to, at a certain threshold temperature and pressure, there's a tendency for the positions of those atoms to shift their arrangement, and that scaffolding to reconfigure itself in such a way that it forms a new and distinct structure. And that structure oftentimes gives rise to drastically different physical properties. And so one common example of this type of phase transformation that people may be familiar with is the transformation between graphite and diamond, where both graphite and diamond are both composed of elemental carbon, but graphite, which is the structure that is stable on the surface of the Earth, is well known to sort of have a soft and flaky structure, which is why it works well as pencil lead, because it sort of flakes off onto your piece of paper. And as it turns out, that flaky, soft structure arises from the atomic level crystal structure of the material, where in graphite we sort of have this planar structure of hexagonal carbon sheets that the material is made out of. So it turns out that these sheets sort of slide past each other readily, which is why it sort of can slide off onto your paper in a sense. But if we subject graphite to the intense pressure temperature conditions that you might find in the deep Earth, there is a tendency for the structure to reconfigure itself in a way that it forms a tightly bonded 3-dimensional network, otherwise known as diamond. And as you may well know, diamond has very different properties than graphite, and one unique property of diamond is that it's actually the hardest material. And so in order to transform graphite to diamond, it takes around 20,000 atmospheres, where an atmosphere is simply the pressure that we experience in our day-to-day life on Earth as a result of the air or the weight of our atmosphere above us. And so 1 atmosphere corresponds to 14.7 psi, or pounds per square inch. And as you may be able to tell from that unit, a pound per square inch, pressure simply describes a force applied over a unit area. So when we talk about increasing pressure, we can sort of take one of 2 routes, the first being increasing the force, and then the second being reducing the area. So one common way people sort of conceptualize the idea is considering whether it would be better to be trampled by an elephant or a woman in stilettos. And it turns out that you'd actually be better served to be stepped on by the elephant, and that's simply because the elephant has such large feet that that weight of the elephant is outweighed by the footprint that that force is exerted over. Of course, the worst case possible scenario would be if you were to be trampled by a herd of elephants in stilettos, but I did sort of a back of the envelope calculation, and this could be wrong, but I think that an elephant's weight on a stiletto might give you around 0.5 GPa, which is still not enough force to transform graphite to diamond. So that's too bad. But it turns out that there are other ways that we can get to extremely high pressure in the laboratory. And these are sort of the techniques that in many senses have been pioneered over the last 50 or so years here at Geophysical Lab. And you can sort of think of these types of techniques as the equivalent of the elephant and the woman in stilettos, where with these sort of large volume presses, we're increasing the tonnage in order to get to higher pressures. So this shows a photograph of the large volume press here in the other building at Geophysical Lab. And with this type of technique, we can generate static pressures up to around 100 GPa, which is impressive in that that's around 1 million atmospheres. But again, as it turns out, the alternative technique, which is sort of analogous to the woman in stilettos, called a diamond anvil cell, you can get to substantially higher pressures. And in this technique, what you're doing is you're reducing the area by squeezing a sample between the tips of two diamonds, in which case you can get to a very high pressure of around 300 GPa, which starts to approach the pressure that you might expect to see in the center of our own Earth. And so while these types of static compression techniques that take advantage of different types of presses to generate large pressures in the laboratory have produced a lot of amazing science, actually my research focuses on sort of a different vein of study, which falls under the umbrella of what's generally known as dynamic compression. And so as you might be able to tell from the name, when we do these types of experiments, what we're effectively doing is we are creating a transient high pressure state, which we achieve by sending a shock wave through a material. And so one method which is used in order to do this is using a high velocity cannon-like device. And so this is an example of this type of two-stage gas gun shown here. So this is actually at the Southwest Research Institute in Texas. But how this instrument works is that it is able to accelerate projectiles to incredibly high velocities, and then we're just hitting our sample very hard, which generates a shock that then moves through the sample. And in that way, we're able to generate an, albeit short-lived, but very high pressure state in the material. And so as it turns out, these types of dynamic compression experiments actually have wide application in Earth and planetary science, one of which is it's really a direct route in some sense to study different types of natural impact events. For example, planetary accretion or understanding samples from different impact craters or meteorites. But also because we can get to just immense pressures far higher than you can get with various static techniques, this type of dynamic compression route is an excellent tool to synthesize high pressure phases that we can only find in the deep interior of the Earth and other even larger planets. And so briefly, to take a step back, shockwaves is a word that's kind of thrown around a lot. And so in some sense, I'm sure people are familiar with the idea. But in a technical sense, a shockwave is simply just a traveling mechanical disturbance that, as it goes through a material, has an abrupt step-like increase in pressure, density, and material velocity. And so this sort of cartoon figure here illustrates some sort of train accident that you can think of as analogous to a shockwave going through a material. And so at the top here, we see the impact event occurring. And then after the impact, we see the shock front, shown here, moves through the material at a velocity or a speed that's faster than any of the given component train cars. And then, in addition, we always see in any dynamic compression experiment at later times, we're eventually going to have a rarefication or a release wave catch up with the shock front, which sets the time frame that we can maintain the high pressure state in our material. And so that's sort of illustrated by this caboose sort of expanding backwards in yellow in back direction. And so one way to think about a shock wave is that it's simply the effect of having material not be able or move at a velocity that is too fast for the adjacent material to sort of get out of the way. And as a result, you see sort of a pileup of material in front of the shock front. And so one common example that people have oftentimes heard of is the idea of a sonic boom, which is sort of illustrated here. And this is simply the result of when you have a jet which is moving at a speed which is faster than the speed of sound in air, you then have a buildup of pressure waves in front of the jet. And so then when an observer on the ground hears a sonic boom, what they're hearing in their ear is that discontinuity in pressure as a result of that buildup reaching their eardrum. And so those are some examples of the types of shock waves that people might experience in their day-to-day life, but how do we go about generating shock waves in our laboratories? And as I mentioned briefly before, one technique to do this is using these two-stage gas guns, or light gas guns. And basically, with these large cannon-like devices, we're able to accelerate projectiles to very high speeds, up to 7 kilometers per second, which translates to roughly 16,000 miles per hour. So that's quite fast, obviously. And so basically, how these work is that we have a charge detonation, which is the result of an explosive gunpowder detonation, and that builds up a hot gas, and that hot gas expands, pushing a piston into a gas-filled pump tube, which is full of a light gas, usually hydrogen. And so that pressurizes that light gas to some threshold pressure. And at some point, that pressure exceeds a certain value where we have a rupture disk that bursts. And when that rupture disk bursts, that allows that hydrogen gas to expand into this secondary launch tube. And when that gas expands into the secondary launch tube, it fires this secondary projectile, which we call the impactor. And then that projectile flies down that launch tube at very high velocity and impacts our sample, which in dynamic compression experiments, we have a habit of calling our samples our targets, and any given experiment a shot, for obvious reasons. And so this video here shows a video collected using a high-speed camera by the people at Imperial College at the Institute for Shock Physics. And in this video, it sort of gives you a picture of what these types of experiments look like from inside the target chamber. So in this case, this is the target, which is mounted right here. This junk on the back is all of these diagnostic probes, which are going to collect data during the experiment. And then when we play this, we'll see the impactor fly in from this direction and hit our target. So it's like, boom. And so this is actually a video that captures a time span of around a microsecond. So this involves using an incredibly high-speed camera to capture a video of this quality. And so this is sort of a schematic of the different components of our two-stage gas gun before and after a given shot. And so here you can see that this elongated piston and this smaller impactor correspond to the first piston, and then the impactor that actually hits our target is this much smaller piece. And then here you see this is our rupture disk, and we score it before the experiment so that it breaks cleanly. And then afterwards, we can see it's been burst by the compressed gas. And then finally here, this is our target before and after an experiment. So our sample is actually mounted on the top of this copper piece. And all of these probes here are what we use to collect data during a given experiment. And so if you can't gather this from these photos, these measurements are destructive. And so we're basically obliterating our target in any given experiment. And so as a result, we're forced to replace all of these components for every experiment that we carry out. And so while these gun-based type experiments are really an excellent tool to generate high pressure temperature conditions in the laboratory, they're not the only way that we can use to generate shock waves. In fact, we can actually use high-powered lasers to do sort of the same thing. And in this case, what we do is we use a high-power laser to generate an ablation-driven compression wave in our sample. And how this works is that we affix a plastic layer to the backside of our sample, and then we focus high-energy lasers onto that plastic layer. And that generates an ablation-driven, or a plasma, and that plasma expands out backwards, and that sends an ablation-driven compression wave forwards through the sample based on sort of a rocket-like acceleration effect. And as it turns out, this type of laser-drive compression experiment is really the forefront of high-pressure science, in that we can get to significantly higher pressures than we can with any other type of technique. And so this figure here shows a timeline of various peak pressures achieved using different experimental techniques in the last 100 years or so. And so here, all of these red circles are points from different types of static compression experiments, for example, a large volume press or a diamond anvil cell. And as you can see, static compression has been steadily increasing and pushing to higher pressures in the last 100 years. And the current state-of-the-art experiments can fairly routinely generate a pressure of around 300 GPa, which is, again, close to the pressure of the center of the Earth. But from this, we can also see that in around 1960, gas guns came onto the scene, and they were able to generate significantly higher pressures. And then with the advent of different types of shockwave compression experiments, for example, pulsed power experiments or nuclear experiments, people were able to generate substantially higher pressures. And then, of course, in the last 20 years, we've seen the development of this laser drive type technology, which sits at the top of this figure, being able to generate just immense pressures. And the highest point of all is held by what is the biggest laser of all. And this is sort of a schematic of the National Ignition Facility, which is a very large laser facility located at Lawrence Livermore National Lab in California. And it has an impressive 192 beams and can produce a peak energy of 2 megajoules, which can drive a peak power of nearly 500 trillion watts. And so this is really the monolith of all lasers in the world. And as you can see, it has just a gigantic floor plan where it takes up around 3 football fields. And so this is sort of in some sense, the frontier of high pressure science, being able to generate pressures up to 5,000 GPa, which is really quite impressive. And so why are we interested in continuing to push and push on this high pressure frontier? And one of the main reasons, or at least from my perspective, for doing this is the desire to better understand, for example, the conditions of planetary interiors of very large planets. And so this shows sort of temperature pressure space, and we can see here that with different diamond cell techniques, we can assess pressures up to maybe the center of the Earth. But then there's this sort of large unexplored area that encompasses most of the planets in our own solar system as well as beyond. And in order to explore this area experimentally, dynamic compression is really the only game in town. But of course, the caveat of dynamic compression experiments is that they are incredibly short-lived. And as I mentioned, any of these laser drive experiments generally last only a billionth of a second, whereas the gun-based experiments last closer to a millionth of a second or a microsecond. And so in order to conceptualize this, what I like to do is think about stretching out a second to 32 years, which is fortuitously about how old I am. And so in that analogy, there we go. In that analogy, then, a nanosecond, or the duration of a laser drive compression experiment, would be then stretched to a second. So the ability to capture any data in a laser drive compression experiment is the equivalent then of isolating 1 second in my entire lifetime. So that would be like the equivalent of being like 1 Mississippi over my entire life. Whereas alternatively, if you're talking about a gun experiment, that would be more like isolating 16 minutes, which I think is probably about how long I've been talking. But still, that's pretty impressive, I would say. But in order to do this, what we really need to think hard about is ways that we can develop ultra-fast experimental probes in order to be able to measure anything. Because it's great if we can generate these intense temperature pressure conditions, but really what's the point unless we can collect any data to learn anything about them? And so one common technique that people use in order to collect data on this very fast timescale is a technique known as high-speed velocimetry. And this is actually in many ways very similar to different experimental tools that people are quite familiar with, in that it uses the same physics that is behind the idea of a police officer, for example, using a radar gun to give you a speeding ticket, or also, for example, how they measure baseball pitch speeds in a baseball game. And all of these things rely on a physical phenomenon, which is known as the Doppler Effect. And that's simply the idea that you see a change in the frequency of a wave emitted from a moving source. And so people are probably most familiar with this idea, having heard the siren of an emergency vehicle go by, where it sounds higher pitched as the vehicle approaches and then lower pitched as it drives away. And so that's a result of that bunching up to high frequencies of those sound waves in front of the vehicle. And as it turns out, you can actually be more quantitative about that, and you can use a measurement of the frequency of those waves in order to back out the source velocity. So in that example, the velocity or the speed of the ambulance. And so in order to take advantage of this type of effect in our experiments, what we do is we coat the back of our samples with a thin aluminum layer. So we'd put an aluminum layer right here, and that serves as sort of a mirror. And then we measure the frequency of light that we reflect off that mirror during our experiment. And in that way, we're able to determine the velocity of that surface and see how that evolves as a function of time. And so in order to do that, what we do is we're measuring a frequency of that reflected light. And to do that, we use an instrument called an oscilloscope, which is basically a high sampling device that allows us to measure frequencies. And so in our experiments, when the shock wave arrives at the back surface of that sample that we're looking at, because that's the mirrored surface, we see an abrupt change in frequency. And so we can take this data that we measure with our oscilloscopes and we can translate that to a plot like this, which we call a wave profile. And that's simply a plot that shows the surface velocity of that mirrored surface as a function of time. So in this case, you can see at 200 nanoseconds, we see an abrupt jump up in that surface velocity. And that's associated with the shock having gone entirely through our sample and having reached that mirrored surface. So as it turns out, actually in most of these experiments, we don't actually just coat the back edge of our sample. Instead, what we do is we put a coated aluminum layer in between our sample and a velocimetry window, which is basically something we're looking through at to that aluminized mirror. And usually we use a material called lithium fluoride in order to do this. And the reason why we do that is because it's well calibrated in terms of how it behaves in these extreme conditions. And we use this type of velocimetry window for two reasons. The first reason being that if we have something on the back end of our sample, when the shock reaches the back end of our sample, we don't see an immediate pressure release because we're not releasing into air. Instead, there's something sort of holding it at high pressures for a longer time. But also, we can use our understanding of how lithium fluoride behaves in order to use the material as a calibrant. And so we can use the information about how that velocity changes when the shock reaches the lithium fluoride to back out the pressure density state in our sample itself. And so in order to do this, we develop models, and an example of this type of model is shown here. And so usually what we're after is in order to develop what we call a TX plot, but it's simply a plot that shows the various interfaces in our sample as a function of time. And so this is one of these models that we've developed for a gas gun experiment in which we are shocking our sample up to 50 GPa. So in this case, at time equals 0, that's when the impactor hits our sample. And immediately we see the sample impactor interface start moving. And so that's because the sample is being compressed. But in addition to that, we also see this material shock wave start to travel through our sample as well. And similar to the analogy of the train, the shock wave is traveling through the material at a velocity faster than any given component of that material, which would be moving at this sample impactor material interface velocity. And so here we see that as the shock wave goes through the material abruptly jumps between 0 GPa up to 50 GPa. And then here, at around 200 nanoseconds, the shock wave reaches the backside of our sample. And that's where we see this abrupt change in frequency occur. And that's an effect of this window sample interface, which is the mirrored layer we're looking at with our velocimetry laser starting to move. And so that's when we see this abrupt jump in our wave profile. And then finally, we see the shock wave travel through the velocimetry window, reverberate back, and we see a partial release occur at around 300 nanoseconds, which you can see as a drop-off in the surface velocity. And so basically, we develop these types of models essentially by using the timing information, which we can interpret in terms of shock wave velocities, as well as applying conservation equations and using the known information about our velocimetry window. And we can build a picture that allows us to develop information about the bulk pressure density state of the material as a function of time in our sample. And then, if we proceed to carry out a series of experiments, we can then determine how the density of a material changes with pressure. And furthermore, if we look at this trend that we're able to build, we can identify kinks in this pressure density curve and say that we're likely, in that case, observing a phase transformation to a new crystallographic phase. And so we know there's an abrupt change in density, but it's oftentimes difficult to know what the structure of that high pressure phase is. And so one good example of this is there's been recent velocimetry type experiments where they shock compressed carbon or diamond to just immense pressures up to around 5 terapascals. And they can see that in that case, the carbon atoms are compressed to nearly 4-fold in the case that, in that case, diamond has a density that approaches that of lead. But based on those experiments, they have no information as to whether the diamond structure has reconfigured itself at all. And so it's possible in that case that one, structure has just compressed, but it's also entirely possible that it's formed a whole new phase, which is sort of the equivalent of going from graphite to diamond. And so in order to get this type of atomic level structure information, another technique that we can apply is the idea of doing X-ray diffraction. And in this technique, what we do is we measure an interference pattern which we produce by scattering high-energy X-rays off planes of atoms in a crystal. And as you might recall, a crystal is simply a arrangement of atoms in a repeating manner that extends in 3 dimensions. And so in these experiments, what we're doing is we're measuring the set of plane spacings between different planes that exist within the crystal structure. And it turns out when you have this type of repeating arrangement, any given set of planes can then uniquely identify the crystal structure. So by measuring then the set of planes that exist in the crystal structure, we can interpret that information in terms of building a picture of the structure itself, as well as identifying the density of that crystalline phase. And so basically how these experiments work is that we use 2-dimensional detectors to collect these types of diffraction images. And then any given one of these rings then corresponds to a set of planes in the crystalline structure. And oftentimes what's done with these 2-dimensional images is that they're collapsed down to 1 dimension, where that's basically essentially what you're doing is taking a radial slice of the 2-dimensional images, in which case each ring then corresponds to what turns into a peak in one direction. But still, we can relate each of these peaks to a set of planes within the structure in a process which we call indexing the diffraction peaks. And in doing so, that allows us to build an atomic level picture of the crystal structure. So it turns out this type of X-ray diffraction technique has actually been around for quite some time and was developed in the early 20th century. But in the last 50 or so years, there's been a real advancement in these accelerator-based light sources, which allow us to generate light of an extreme intensity. So usually the measure we oftentimes talk about this type of very bright light in terms of is this idea of brilliance, which is basically just a measure of how much intensity of light you can squeeze into a tightly focused beam. And so I'm going to talk about 2 sets of experiments, one using this type of synchrotron facility. And so these experiments are carried out at a facility called the Advanced Photon Source in Chicago that is based upon a ring-like accelerator. And then the second set of experiments I'm going to talk about use a different type of accelerator facility known as an X-ray free electron laser. And this type of light source is particularly valuable for this type of dynamic compression experiment, and that's because not only does it have far higher brilliance than these other types of synchrotrons, but it also has extreme timing precision. And so it's really very valuable in order to probe our samples on very fast timescales. Okay, and so I'm now going to talk about a few examples of how we apply these techniques to problems in Earth and planetary science. And the first set of experiments I'm going to talk about are using these types of shock compression tools to study the dynamic response of silicon dioxide, or silica. And this work is important because silica is actually the most abundant constituent of the Earth's crust. And so if we're interested in understanding, for example, samples that have been collected at natural impact sites, for example, Meteor Crater in Arizona, understanding how the material responds to shock loading and the different types of crystallographic transformations that we expect to see at various pressure temperature states is really critical. And so this is actually a problem that has been studied quite a bit in the last 50 or so years, but despite all of this study, there's been quite a bit of debate as to what the actual crystal structure phase that forms in silica under this type of shock loading is. And we know from different types of static experiments that there are a wide range of different structures that have been observed, but it remains unclear as to which phase forms when you shock a sample to the conditions you might expect to see in a natural impact event, and at what pressure we expect to see various phases appear. And so in order to answer some of these questions, I carried out a series of experiments using gun-based shock loading techniques combined with pulsed X-ray diffraction. And these are experiments carried out at the Advanced Photon Source Synchrotron facility in Chicago. And how these experiments work is that we have one of these two-stage gas guns that I discussed positioned at some angle to the synchrotron beam. And so actually in this case, the length of the gun is positioned in such a way that the X-ray beam comes in at 30 degrees to our sample surface. And then we scatter X-rays off our sample, and the X-ray detector sits directly behind this target chamber. And you can see here, that's the X-ray detector back here. And that's my collaborator, Stefan, mounting one of these targets here in the target chamber. And then this is the target itself. And in this case, you can see the sample is right here. And as I mentioned, we have an aluminized layer there, plus a lithium fluoride interferometry window. And then all of these probes are designed to measure velocity at various points in our sample. And in that way, we used various velocimetry techniques in order to determine both timing information of our experiment as well as the bulk pressure density state and see how that evolves in time. So how these experiments work, where we're combining diffraction with shock loading using gun experiments, is that when the incoming projectile approaches our target, there's this laser interrupt. And so when the projectile interrupts that beam, that then instigates the gated collection of a series of X-ray diffraction frames during the loading and release process. And as it turns out, the synchrotron beam doesn't deliver a continuous beam. It actually delivers a beam that arises in a series of pulses of intense light. And those pulses are separated in time by roughly 150 nanoseconds, which actually is quite good for these experiments because it provides a good sampling rate over which we can sort of collect a series of 4 frames during our experiment. And so this shows an example of a shock compression experiment in which we are shocking silica glass up to 50 GPa and then collecting 4 diffraction images as the shock wave goes through the material. And so in this case, this first frame at the very top was collected just right before the impactor hit our sample. So we're seeing just a signature of silica glass. And then this second frame, the shock wave has gone partially through the material, and we start to see some emergence of features which suggests that we're seeing a phase transformation in the diffraction data. But it's really this third frame, when the shock has gone entirely through the sample, yet hasn't started to release yet, where we see the emergence of these clear X-ray diffraction rings, indicating that the material has crystallized. And then finally, this last frame, we see a broadening of those rings and sort of a shift, which suggests to us that the material is starting to release back to ambient conditions. So in that case, the shock has gone entirely through the sample, and the release wave is starting to come back in. And so if we look at the results of that third diffraction image we took, where the material is shock compressed to a state of 50 GPa, and look at the one-dimensional diffraction data that we can derive from that two-dimensional image, we're able to analyze this data to understand that the material is transforming to a high-pressure phase known as stishovite, which is shown here. And in stishovite, as opposed to the lower pressure phases of SiO2, each silicon atom is surrounded by 6 oxygen atoms rather than 4 oxygen atoms in ambient conditions. And so using these types of experiments, we're able to resolve this question as to what the high pressure phase of SiO2 under shock loading, which has been a question of some debate for many years. And so we're able to sort of harness the unique capabilities of these types of ultra-fast measurements to answer this type of question for the first time. So now I'm going to change gears a little bit and talk about a second set of experiments in which we use laser drive compression to understand the high pressure temperature behavior of a material called silicon carbide. And these experiments are motivated in part because of the recent discovery of thousands of these extrasolar planets that are around other stars in our galaxy. And so as a result of this discovery, there's been a lot of questions raised about understanding the formation and evolution of different types of planetary bodies that may look very distinct from our own. And in particular, it's believed that with planets that orbit stars that have a high carbon to oxygen ratio, you'd expect to have worlds formed in which graphite, carbides, and diamonds would be the primary component rather than the silicates that we observe in our own Earth. And as a result of the fact that these style of carbon planets are expected to have a thin diamond layer in them, they're oftentimes dubbed diamond planets in the popular media. But actually, as it turns out, the bulk of the interior structure of the mantle of these types of carbide worlds would in fact be a material called silicon carbide, which is actually oftentimes used as a synthetic diamond substitute in cheap jewelry. But as a result, we're really interested in understanding the high temperature pressure behavior of silicon carbide at the conditions that are relevant for understanding the interior of this type of planet. So in order to do this, we carry out a series of laser drive compression experiments at the X-ray free electron laser. And these experiments are called pump probe X-ray diffraction experiments. And how this effectively works is that we have a suite of identical silicon carbide samples. We mount these samples on a translatable cassette. And then we use two high-powered pulsed lasers focused on any one of those given samples at a time, and that sends a shock wave through that sample. And then what we do is we collect a series of shots where we collect X-ray diffraction data at different probe times after the shock has entered the sample. And so in doing so, we're able to take advantage of the exquisite time resolution of the X-ray free electron laser to sort of build a picture that you can think of as a series of snapshots as the shock wave goes through the material and during the subsequent release process. And so this is sort of one of such of these time series that was collected for a series of shots in which we're shocking the silicon carbide up to a pressure of 200 GPa. And in this case, I'm showing just this top detector, where in these experiments, we're actually using 6 detectors surrounding the incident beam in order to capture the full diffraction rings. So here, we're only seeing these arcs, which correspond to sort of a partial part of that ring. And is that playing? Yes. In these videos, we can see very quickly, within a nanosecond, the formation of these bright diffraction lines, which correspond to a new phase crystallizing very quickly. And then furthermore, as the shock wave breaks out of the backside of our sample, we see those lines shift, which is the result of that crystalline phase expanding as pressure releases. And finally, at later times, we see it revert back to the ambient phase that we observe at ambient conditions. And this is all occurring within a period of like 14 nanoseconds. So this transformation and back transformation is impressively fast. And so if we analyze this data, we can understand that transformation, not dissimilar to the transformation we observed in silica in terms of a transformation to a crystal structure known as the rock salt phase. And it's called the rock salt phase simply because it has the same crystalline order as table salt, which is just NaCl. So it's the same structure, but in this case, the atoms that make up the structure are silicon and carbon. And so at ambient conditions, silicon carbide is composed of a structure in which each carbon atom, or each silicon atom, is surrounded by 4 carbon atoms. But through this transformation, it goes to this rock salt phase in which each silicon atom is surrounded by 6 carbon atoms. And So that's kind of similar to what we observed in silica, although in this transformation, the volume collapse which is associated with the transformation is far larger than the volume collapse we observe in silica. And so as a result, it has a more substantial effect on the understanding we have in terms of how these types of carbon planets might evolve in such a way that we expect this phase transformation not only to occur at deeper pressures, but also to have a substantial effect on the layering and different types of flow patterns that might develop in this type of carbon world. And so using these types of techniques, we're able to understand that these types of carbon worlds most likely evolve in a way that's very distinct from our own silicate Earth, which we're more familiar with. And so I think with that, I will wrap up. And I sort of created this montage of different photos that were taken during various experiments to sort of give you a flavor of what this looks like. And I thought I'd just leave this here and take any questions.
Thanks, Sally. What's
Sure.
the pressure here? Happy to entertain questions.
Given that your experiments are, they cost money because you have to throw away stuff, the ones that you have to throw away. So how many times do you repeat the same exact experiment that you can center on results that I can imagine there's variances and stuff.
Mm-hmm.
You must do a certain number of exact repeatable things to data is good. So how many exact experiments of each one do you do?
So that depends a lot on whether if what we see is kind of what we expect, or if we see something that we don't understand, we oftentimes will reproduce an experiment in order to trust our results. But oftentimes what we're doing with these measurements is we're sort of taking steps, for example, up in pressure, and so we can identify sort of trends, and we see trends evolve, in which case if we sort of understand what we're seeing, we generally only will do it one time. But if we see something new or something we don't understand, we certainly always will go back and see if we can recapture that.
I'm just curious, to what extent can you use calculational tools for, particularly the one example you showed, it looked like you transformed into a phase and then you reverted back.
Sure.
So that the phase clearly wasn't stable.
No.
Does that correspond to what you would get out of a calculation? I don't know at what level you have to do a calculation to get that kind of information, but it would seem like it's not impossible to do those kinds of calculations.
No, it's not. And in fact, oftentimes we either carry out calculations ourselves or work closely with other experimental groups that focus primarily on carrying out the calculations. The problem in many cases with various types of calculations of crystal structures is while they may be accurate, oftentimes they're way off in terms of where they predict a transition to occur, for example, in pressure. And so in many cases, especially when we start to get to ultra-high pressures, there's a wide range of predictions as to what we expect to occur, but without any experimental validation, there's really, we really need the experimental data to back up, especially when you have conflicting calculations, but to better understand what's actually occurring.
I know in explosives there are methods of using lensing to focus the shock wave.
Mm-hmm.
I just wonder if these sort of pressures, and is that possible at all with some sort of tamper?
So one thing that we do quite a bit of is we tune our laser pulse shapes in order to produce different, for example, mostly rise times of the laser pulse shape. So in that way, we can sort of control, one, the shape that we get, but also the rise time, which is actually really critical in terms of controlling the temperature. And so one way that you do that is you can build different combinations of sort of shocking and then trying to push more slowly to sort of control the thermodynamic path which you assess in pressure temperature space. And so actually quite a bit of modeling and effort goes into designing and tuning the laser pulse shapes in order to get to the pressure temperature condition and drive that condition for the desired amount of time such that we can match our drive to our X-ray source so that we get, or at least understand, what we're looking at. And so that's something that there's quite a bit of effort that goes into.
Your light gas gun, you said gunpowder, but there are other propellants that have far more energetic impulses, such as gases that are ignited.
Sure.
Are you up into those type of things?
No, so generally what's used is pretty standard gunpowder in these experiments. I think maybe the idea of exploring various other explosives could potentially get to higher pressures. I don't know. It's not something I've thought about. Of course, in these experiments, safety is always in the forefront of our minds, and being able to have a well-controlled explosive that's well-calibrated is critical. And so,
This is basic artillery, and artillery science is pretty old.
Sure.
And artillery science has advanced way past nitrates.
Well, I mean, I'm not an expert in artillery science, but I'm sure you're right, and I'm sure that it's probably something that people have thought about, although is not my area of expertise.
My question is actually kind of a follow-up to that, and which is, I was taken by your chart of how things have progressed over the past 100 years. Where is it going? What will be the kinds of experiments and the ways they are being done in 10 years, 20 years? What's the future?
Yeah, well, I think that that's a really interesting question, in that I think that there is so much work to be done primarily on the side of being able to develop experimental probes to look at these materials. And so, X-ray diffraction is just one way to look at materials. For example, we can do other types of spectroscopy which give us additional information about the various phase transformations or structures that are forming. And so being able, one, to do a better job at collecting data on this very fast time frame with the pressures that we're at is an enormous job in and of itself. But of course, I think that there'll continue to be advances in high pressure science in terms of pushing it to higher pressures. But as I was sort of mentioning in this gentleman's question, one of the big forefronts in this field is being able to control the temperature. Because in a lot of these experiments, we're just heating up way too quickly and melting our material. So if we want to maintain a colder solid phase up to high pressures, that's one type of experimental study that is in the current experiments, something that people are really interested in refining and doing better.
I've heard that people are making diamonds. Now, what you're doing, it looks like you get pictures. And are you actually making any substances as an end result of what you're doing, or you got pictures and you're looking at the pictures and analyzing that?
So people do shockwave experiments that are targeted at actually recovering the sample in order to look at the end product results. And the experiments I talked about today were not doing that. And depending on the pressure temperature state you achieve, in many cases, our samples are like vaporize and melt on pressure release. And so there's really no way to recover them. But there is quite a bit of work at lower pressures focused on understanding and recovering samples and looking at various metastable phases that might form, for example, and better understanding the structures and various microstructure features that they observe as a result of the shock loading process.
Take two more questions, one here and one back here.
Just a follow-up to the synthetic diamonds. Are they made using any of these high-pressure techniques, or how are they created?
So there's actually several ways that people can create synthetic diamonds. I think the best way currently is actually using a technique called CVD, where they're using a substrate and depositing carbon onto that substrate such that it takes on a crystalline arrangement more similar to the substrate. So you're sort of tricking the carbon atoms into forming a structure that otherwise wouldn't be stable. That said, of course, you can certainly form diamond by shocking graphite. It just might not be the most effective or cost-effective means of doing so.
We do make them in our lab. We often use graphite as a heater in those large volume presses, and diamond is something we try to avoid, and it actually ruins our experiments.
Is the work done on the Cherenkov effect? Does that have any application here?
I'm sorry, I couldn't hear what you said.
The Cherenkov effect. Is there anything that's analogous to that could be applied here?
I'm not sure if I know what that is.
Cherenkov effect is if you have particles going faster than the speed of light for that medium, and it produces like a bluish color in a nuclear reactor.
Yeah, I mean, I'm sure that is probably something that certainly comes up in experiments. For example, experiments they carry out at NIF, which was actually designed to do fusion experiments, not to do the experiments that I was talking about today. Although we're not specifically targeting investigating that with our studies.
Okay, if there's no more questions, I would like to thank, one more question?
So, well, the material, what's being shocked is the crystalline material itself. And so we can have it in a vacuum. And in fact, although it's a rough vacuum, in these experiments, we're generally pumping down the target chamber before we do the experiment. Because it's not the air that's experiencing the shock wave, it's the crystalline solid that's shocking.
So if there's no more questions, one more question. All right, I like you guys.
This is about what the results would be from phasing. If you have a material like graphite, you turn it into diamond, is it denatured? In other words, you can't change it back?
Well, I do think that you're able to quench at least small amounts of diamond in these types of experiments. It wouldn't be the large grain crystalline diamond that you would use for other purposes, but in recovery experiments and even at natural impact craters, they do observe very small micro-sized diamonds that are as a result of the carbon in the rock being shock loaded.
But they can't be changed back to graphite.
I mean, likely if you were to
like
heat
an egg.
treat
You
those
cook an egg,
diamonds,
you can't change it back.
it would revert. I mean, that's a question of the material being locked in the diamond structure and the kinetics not wanting to transform back, although it's more stable in the graphite structure. If you gave it some energy, for example, by heating it up, it would likely want to go back to the more stable form, which is graphite.
Well, thank you all so much for coming, and thank you for those great questions. And I was going to ask you to thank Sally one more time, but you've already done that. So good night. Thank you very much.